Yes, we can talk about after class about anything. Better time to talk about it than now. All right, so let's go through. Why is there this weird line on my screen? Ay. All right, so now you guys can see my screen and I can see my screen, so we're both happy, or at least I'm happy. Maybe you guys aren't yet. All right, so let's go into the stuff today. No real announcements. Let's just get started. So last time you'll recall that we did VSCPR, which is a way for us to determine the three-dimensional shapes of molecules. And one of the key things that the three-dimensional shape allows us to determine is the polarity of the molecule. So to talk about the polarity of an entire molecule, we first need to review what it means for an individual bond to be polar. This is a topic that is covered on the current exam, so this will serve as a little bit of a refresher. So recall that when you have a polar bond, you have both the direction of the polarity, which is indicated usually by an arrow or by partial negative, partial positive, and that's going to be towards the more or less negative atom. And so basically the direction of the polarity is where is there more negative charge on average. That's going to be towards the more or less negative atom. So for example, if we have this very common polar bond HF, we would draw the bond polarity either as an arrow or more commonly as a delta plus, delta minus, indicating that there's more negative charge on fluorine than hydrogen because fluorine is more electronegative. So that's sort of the direction of polarity, and then the magnitude of polarity, in other words, how polar is the bond? Is it just a little bit polar or a lot polar? That depends on the difference in electronegativity between the two atoms. So those are the two things that determine whether a bond is polar, or how we sort of talk about bond polarity, the direction and magnitude of that polarity. And then if you want to talk about the molecular polarity, the polarity of an entire molecule, for the definition of that, remember that polarity refers to an uneven distribution of charge. And so far we've only talked about that in the context of just two atoms bonded to each other, one being more electronegative than the other. If we have a larger group of atoms, more than just two atoms, as we would in most molecules, a molecular polarity, a polarity of an entire molecule, would indicate an uneven distribution of charge over the whole molecule or a large portion of it. All right, so molecular polarity it's a very similar definition. It's an unequal distribution of charge, but this time we're talking about the entire molecule or a large portion of it. So it's over sort of a larger range in space. All right, so it means your molecule is going to have some region where there's more negative charge, some region where there's more positive charge. The units for that, which is not terribly important, but just to be familiar with it, we're not going to do any quantitative problems dealing with polarity, is measured in a unit called debye, D-E-B-Y-E, with abbreviated as capital D. And this is because polarity is sort of a product of charge and distance. It's given as a compact unit, which is 3.34 times 10 to the minus 30th Coulomb meters. So molecules are very small and the absolute value of their charge is very small. So debye, which is sort of the unit of polarity for a single molecule, is a very small number. C here being coulombs, which is the standard unit for charge. But like I said, we're not going to be really doing anything with measuring polarity, but that would be the units that are used to describe it if you wanted to start talking about it quantitatively. But then to understand whether a molecule is polar or not, there are two things we need to think about. So one is that it must have polar bonds. So what that means then is that most homoatomic molecules, in other words, molecules that have just one type of atom in them, these would be nonpolar because they don't have polar bonds. So N2, P4, S8, etc. Because they have all the same atoms bonded to each other, none of the individual bonds can be polar, and that means the whole molecule cannot be polar either. So these ones cannot be polar if they have just one type of atom in them. So in order for a molecule to be polar, it has to have polar bonds, meaning it has to have atoms of different electronegativities in the structure. That's sort of the first criterion. But having polar bonds, if you want to use sort of the legal terminology, having polar bonds is a necessary but not sufficient criterion for being a polar molecule. So you also have to think about the geometry of the molecule. And basically what happens, and we're going to talk about this in more detail, but the presence of polar bonds does not guarantee that the entire molecule will be polar. So it is possible, as we'll see, to have polar bonds, but to have a molecule that itself is not polar. And that's going to be determined by the geometry of the molecule. So we learn how to determine the three-dimensional shape of a molecule using VSEPR, and that three-dimensional shape is going to be key for deciding whether or not the molecule is polar. If it has polar bonds, it could be polar, but it's going to be determined by what that geometry is. All right? And so then the key thing we have to think about then is in a molecule that has polar bonds, we have to decide whether the individual bond dipoles, whether or not they cancel each other out. Because in some geometries, all the bond dipoles are going to be equal in opposite direction. They're going to cancel out to have zero net polarity. In other geometries, they won't completely cancel out, and then you'll have a polar molecule. So it's a pretty common situation to have polar bonds but have an overall non-polar molecule. And this is the situation when individual bond dipoles, so each individual bond is polar, but the individual dipoles cancel each other out. Now, I'm going to give you a case where this is very common and one that you're going to want to look for in homework questions and test questions, because it's one that comes up a lot in the general chemistry course. This would not be the only time when this is true, but a time when it certainly is going to be true is if you have an AXME0 molecule. So what this means is you have one type of outer atom X. So it's the typical AXE notation we're using for VSEPR with the central atom A, some atoms bonded to the central atom, and some number of lone pairs on the central atom. In a situation where you have AXME0, which means you have one type of outer X atom and zero lone pairs on the central atom, those will all be nonpolar. All right, and I have to be careful that all these criteria are true. Only one type of outer atom X, all the X's are the same in the formula, no lone pairs on the central atom, meaning it's an E0 type structure, the E part being 0, those will be nonpolar. So some classic examples of this would be if you have CO2, which is AX2E0. This one's pretty easy to visualize. So in carbon dioxide, leaving out the lone pairs on oxygen, we would have a dipole that goes left to right from carbon to oxygen being more or less negative than carbon, but then exactly 180 degrees from that, because it's a linear molecule, we have another dipole going right to left. I should have drawn on the same size, because ideally they are, so let's try to do a little bit better job of that. But basically, we have two identical dipoles that are equal but opposite in direction, and they cancel out. And so the whole molecule then is nonpolar, because the dipoles cancel out. Another way to draw this would be you would have a delta minus here, a delta minus there, two delta plus on the central atom, but in that you have no uneven distribution of charge because the dipoles in both directions cancel out. So this whole thing would be nonpolar, even though it has polar bonds. Or similarly, BF3, this time I think a little bit more two-dimensionally, BF3 is AX3, and so you'd have a dipole going in this direction, and this direction between each boron-fluorine bond. But if you break these vectors down into their x and y components, which we're not going to do that mathematically, but you could, they would all cancel out to 0. Yes? So a dipole means it has polarity. So basically it means it has an unequal distribution of charge. So these two molecules here are nonpolar because the individual bond dipoles that they have all cancel each other out, and in net there's no dipole for the whole molecule. So basically we're adding up all the different dipole vectors that you have, and if they add up to 0, that means the whole molecule is nonpolar, which is what you'd have for these two examples here, or any case when you have no lone pairs on the central atom, all the outer atoms are the same. All those basic electron group arrangements we talked about, linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, octahedral, in all 5 of those cases, if you had polar bonds at each position, they would all cancel each other out, and the whole molecule would be nonpolar. Okay? All right, so that's going to be the situation for those ones where you have polar bonds, but the molecule itself is nonpolar. But of course, there's many examples where the molecule is polar overall while having polar bonds. And so this occurs when the bond dipoles do not cancel out. Again, not an exhaustive list of when this happens, but a common one would be AXME1. One lone pair on the central atom. You can bet whatever piece of property is most precious to you that this is going to be polar, okay? So anything with one lone pair on the central atom is polar. Now, again, this is not the only case where that's true, but that's a very common one we'll see in VSEPR, and one that you can quickly identify. If there's one lone pair on the central atom, it has to be polar. All of those geometries, AX2E, AX3E, AX4E, AX5E, in all those cases, the bond dipoles do not completely cancel out. There's always one that's opposed by a lone pair, and that lone pair doesn't have a dipole associated with it, so that one dipole would not be canceled out, or at least one, and that gives you then a net molecular dipole. All right, or another one that's very common would be water. So if we have H2O, this one has two lone pairs now, but as we said last time, water is bent shape. And in this case, it does have the two lone pairs on the oxygen, but I'll sort of draw in his little bunny ears, but we don't need to worry about those for polarity necessarily, we just need to know the shape. And in this bent geometry here, we have oxygen is more electronegative than hydrogen, so we're going to have a dipole that goes from each hydrogen to oxygen. These actually reinforce each other in some sense, because we're putting two dipoles together like this. The x components kind of oppose each other, but then there's a reinforced y component in the vertical direction as I've drawn it here. So these dipoles reinforce each other in the y direction. And what you'll get, and again, we're not going to worry too much about defining the direction of the dipole. Our main concern is it polar or is it not polar? Not worrying too much about the size or direction of the dipole. But in this molecule here, OH2, these two dipoles would add up to give a net dipole for the whole molecule that is oriented vertically, as I've drawn it here, where basically there's going to be an uneven distribution of charge, partial negative up by the oxygen, partial positive down here between the two hydrogen atoms, which are less electronegative, and an unequal distribution of charge over that whole molecule, making it a polar molecule. All right, so, and we talked last time about there's a lot of categories of molecules that have AX2E whatever, where it's just three things, a central atom and two atoms bonded to the central atom, and there's only two possible geometries, linear and bent. If it's linear, it's nonpolar. If it's bent, it's polar. So again, another easy one to help us remember. I'll give you a whole table on this at the end to summarize it all, but those are some that we want to sort of focus in on. Now, there is a possibility, though, that you have to think a little bit more than just the basic shape to understand the polarity, okay? So in some cases, you can have let me not write that again. So we have same basic shape, same polarity. So let's do this one here. Let's do CCl4. Now what we would predict for this one is that it's going to be tetrahedral. Now, we said earlier that if you have a molecule that has four or all the same atoms bonded to the central atom, these are all chlorines, and it has no lone pairs on the central atom, so this would be AX4E0 if we want to include the E part of it, this would be a situation where it's nonpolar, and that's certainly true. So carbon tetrachloride, CCl4, is nonpolar. Now, however, though, what if we had CH2Cl2? So it's still going to be technically AX4, but now we have two hydrogens and two chlorines. So we'd have C, and then two of those are going to be hydrogens, two of them are going to be chlorines. Now, technically speaking, you could classify this also as AX4, but really it's more like AX2, X prime 2, because we have two different outer atoms. We have two of one type, which is chlorine, two of another type, which is hydrogen. This is still tetrahedral, but then if we look at the bond dipoles in this guy, we're going to have dipoles from carbon to chlorine going that way, and then you're going to have smaller bond dipoles going the other way for hydrogen and chlorine because carbon is a little bit more, sorry, for hydrogen and carbon because hydrogen is a little bit less electronegative than carbon. So the point is these dipoles, they're not all the same in size, they're not all in the opposite directions from each other, so they don't cancel each other out, and this molecule would be polar with a net dipole that sort of goes towards the more electronegative chlorine atoms like that. Again, the exact direction of the dipole not so important, but the point is that this molecule here is polar. So they're both tetrahedral, but because one of them has the same 4 outer atoms, that makes it nonpolar. When you have 2 different outer atoms, AX2, X prime 2, or if it was just AX3, X prime 1 with 1 hydrogen and 3 chlorines, for example, in that case the dipoles don't cancel out and the molecule is polar. So those are some ones that are going to be commonly coming up. That should be CH2Cl2, my bad. All right, so they're both tetrahedral, but one's polar, one's nonpolar. All right, so then as a review of the last 2 sections, VSEPR and polarity, let's go through several examples. It's not really meaningful to talk about the polarity of an anion. They're always polar because they have negative charge. So let's just talk about the shape of CO3 2-. So remember that to get the molecular shape, we have to start with at least a decent approximation of the Lewis structure. So for CO3 2-, I'm going to skip some steps that we should already know how to do, but there's going to be all right, we're going to have 6 plus 18 is 24 valence electrons. All right, so if we go through the Lewis structure of CO3 2-, what we should get is something like this. Now, technically speaking, we should have 1 double bond to complete the octet of the central atom, but it doesn't really matter for VSEPR whether we have that at all or which position it's in. So this is what you would get for CO3 2-. And then if we want to predict the shape of CO3 2-, remember we're going to classify this in AXE notation, which is from the standpoint of the central atom. We can get from the formula CO3 2-, that there's 3 things bonded to the central atom. And then there's no lone pairs on the central atom. There's a lot of lone pairs on oxygen, but what we care about for the shapes of molecules is the central atom. So it's going to be AX3E0 or just AX3. And so if it's AX3E0, that's going to be a trigonal planar electron group arrangement and a trigonal planar molecular shape. Remember that if there's no lone pairs on the central atom, the electron group arrangement and the shape are the same. So there's a table in the last notes that summarize all of these. But that's again what we do. We get a Lewis structure, or at least a close approximation of it, and then we can go from there to figure out the AXE notation and translate that into a molecular shape. So that's how we do CO3 2-. The next 2 here is going to be sort of 2-part questions. We're going to determine the molecular shape and then also determine if it's polar or nonpolar. So like I said, there's some details in there about molecular polarity that I threw in you, things about the direction of the dipole moment and cancellation of dipole moments in individual bonds. Those are a little bit more advanced than we might necessarily need. In general, what we're going to have to do in this course is if we give you a molecule, you're going to have to predict, is it polar or nonpolar? That's kind of the dividing line you have to be able to draw. So we'll do that for a few of these. So PCl5, polar or nonpolar? So in PCl5, the Lewis structure would look like this. I'm going to skip a lot of steps for doing Lewis structures because that should be old hat by now. I don't believe we did PCl5 before, but what you get in that case no lone pairs on the central atom once again. So this is going to be an AX5E0 structure. All right, so because it's 5 electron groups, that's going to make it trigonal bipyramidal. So if we want to draw this more accurately, we would draw it like this, with a triangular base for 3 of the chlorines, and then the other 2 in the apex above and below this. So we call this molecular shape trigonal bipyramidal. So that would be the molecular shape for this molecule. Again, because there's no lone pairs on the central atom, the molecular shape and the electron group arrangement are the same. But then if we want to know if it's polar or nonpolar, this is one of those situations where we have 5 identical outer atoms, no lone pairs on the central atom. And so because it's AX5E0, that also tells us that this will be a nonpolar molecule as long as all the outer atoms X are the same, which they are. They're all chlorines in this molecule. All right, so those are the classic example of a nonpolar molecule. When you have no lone pairs on the central atom, that's typically going to be the case. All right. And then if we do IF3, the shape of this one's a little bit weirder. So if we have IF3, the Lewis structure that we get, skipping a lot of steps again to save some time, keep us on track. We're going to end up with 2 lone pairs on the central atom. Okay? All right, so we want to first determine the shape of this. So in the central atom here, we have 3 fluorines, so it's AX3, and then what we found out from drawing the Lewis structure is that there's also 2 lone pairs. So the AXE notation for this molecule would be AX3E2, 3 atoms, 2 lone pairs on the central atom, a total of 5 electron groups. Because it's 5 electron groups, they're going to arrange themselves as a trigonal bipyramid, but then 2 of those are now going to be lone pairs. And as we said last time, for the trigonal bipyramidal structure, whenever you have lone pairs, they all go onto the triangular part, the sort of central part of the molecule there. And so we're going to put those 2 lone pairs anywhere really on this triangle, but we'll put them there, and that's going to leave fluorines here, here, and here. So you'll recall this is sort of shown on its side here, but this shape here is called T-shape. So the AX3E2, 5 total electron groups, 2 of those 5 positions occupied by lone pairs leaves the other ones in a T-shape arrangement. So that's going to be the shape. Now, to determine if this one is polar or non-polar, again, there's, a lot of you are going to be tempted to just memorize the table I give you at the end, but let's try to think about it a little bit conceptually. So in this molecule here, we have a bond dipole. So fluorine is more electronegative than iodine, so it's going to be a dipole going vertically like this. There's going to be another one that goes vertically pointing down towards this fluorine. So those 2 basically cancel each other out. They're equal in opposite direction. But then we also have another iodine-fluorine bond that goes in this direction. And this dipole here is not going to be canceled out because there's just lone pairs on the other side. So in this case, we would expect there to be a total molecular dipole from left to right, as I've drawn it here, towards this side of the molecule. Again, the direction not being important. We just want to know, is it polar or nonpolar? In this case, the 3 IF bond dipoles do not cancel each other out. These 2 basically do, but this one is not canceled out by anything, so that makes this whole thing polar. Okay? Now, any AX3E2 molecule would be polar. That's going to be certainly true for any molecule that has that shape. But we can use the, once we know the 3-dimensional shape of the molecule, we can use that to help make that prediction. All right, and then finally, last one. As I said, one of the fun things about this chapter is we can start talking about molecules that have noble gases at the center, which is not very common, but certainly is out there, and that gives us some cool shapes. So if we do XEF4, we can go through this one a little bit more deliberately since it's a bit of a more involved one. So xenon, if we're dealing with noble gases, those are, as we said, in group 8 on the periodic table. Oops, wrong PDF. So xenon is here. It's a group 8 element, so it would bring in 8 valence electrons. And then it's going to be bonded to 4 fluorines that each bring in 7. So when we count valence electrons for this guy, we're going to have 1 xenon that contributes 8. And then we have 4 fluorines that contribute 7 each. So a total of 36 valence electrons. So you should be able to get to the Lewis structure by now. That's still covered back in chapter 3 and is on the first test. So to do the Lewis structure for xenon tetrafluoride, we start with single bonds to all the fluorines. We complete their octets. All right, so we have 4 fluorines with complete octets. That's 32 electrons. We had 36 total in this molecule, so that means we have 4 left. That means they're going to all go on the central atom now. So we're going to put 2 non-bonding pairs or 2 lone pairs on the central atom of xenon. So that would be the correct Lewis structure for xenon tetrafluoride. And then translating that into the AXE notation, that's going to be AX4, 4 fluorines bond to the central atom, E2 for the 2 lone pairs, okay? We have a total of 6 electron groups. 4 plus 2 is 6, which means this is going to go into an octahedral electron group arrangement, which is a square-based bipyramid is another way to think of that. And in this AX4E2, we want the 2 lone pairs to be as far apart from each other as possible, so we put them on opposite sides, and then we're going to put the other 4 with fluorines. And as you'll recall, these 4 fluorines just make up a square along with the xenon, and so we would call this square planar geometry. Okay? So that's square planar, and then to decide if it's polar or not, it might be helpful to draw this in the side view, which would be just, remember, we don't really have to think about lone pairs for polarity. We can just draw them. And what you'll see for xenon tetrafluoride is the noble gases don't really have well-defined electronegativity values, but fluorine is the most electronegative atom in the periodic table, so we expect the dipoles to go towards fluorine. We have this one, but it's going to cancel out with that one down there that's 180 degrees apart. We have a dipole between this xenon and the fluorine on the right that goes from left to right. Then we have an opposite dipole going from right to left towards that other fluorine. And so basically this is almost like 2 superimposed linear molecules where all the 4 dipoles cancel out, and this whole thing then would be nonpolar. All right, so square planar is the geometry. Then because it's square planar, the 4 bond dipoles completely cancel each other out. You have 2 pairs that are each 180 degrees apart that cancel each other and leave you with no net dipole. All right, so that goes through a lot of examples of how to use VSEPR to find the molecular shape and then translate that into a polarity. This here gives us a summary of molecular polarity that, again, I don't think your goal should be to memorize this, but hopefully to use it to sort of help guide you as you're learning this and recognize some patterns. The key thing is that for this table to work, all of the x's in the AXE notation have to be the same. So it only works when you have a center atom with one type of outer atom, where this is going to be universally true. And as you'll see here, in all of the geometries where there's no lone pairs, it's nonpolar. In all the geometries where there's one lone pair, it's going to be polar. That's true whether or not the x's are the same, as it turns out. And then for the rest, it's sum of each. You have to kind of look at those ones more closely, as we saw for some of these last examples, to figure out if they're polar or nonpolar. But all of the information is summarized on this table. And like I said, the vast majority of molecular polarity questions that you're going to come across in homework assignments and tests are going to be sort of typical AXE structures like these, where you have a well-defined central atom and some type of outer atoms, and then you're going to basically just be predicting whether or not it's polar. Is it polar or nonpolar? That's really all you have to be able to figure out. All right, so any questions on those topics before we move into something a little bit different? Yes? Would you ever have to do the polarity for a molecule that has more than one central atom? I would say in rare cases, the one example might be like some molecules like this that have like 2 carbons bonded to each other. I don't think your book really covers this in much detail, but if we were to like draw this structure here, stuff like this, you'd have to decide this molecule is totally flat because both sites are AX3, and the dipoles in this case don't cancel each other out because you're going to have a net dipole. But it won't get anything more complicated than this. We might go over some like practice problems with that later on, but it's going to typically, for polarity especially, it's just going to be things that have a single central atom. Now, what we're going to talk about in this next section, though, is we're getting into, if there's any other last questions, I'll handle them now. In the next section, we will often deal with molecules that are more complicated, but we're still going to do it from the reference point of a central atom. Were there any other last questions on that? I kind of looked down for a second. Yeah.
Could you go back a few slides? I wasn't able to, I think it was when we were talking about the molecular polarity right after the review of photons.
Here?
Okay,
so the key point I wanted to make here, I went through it in more detail a little bit as we walked through this, was that the presence of polar bonds does not guarantee that a molecule will be polar. So a molecule has to have polar bonds to be polar, but just because it has polar bonds does not mean it is polar. So that's where the geometry comes into play to decide whether the bond polarities, the individual dipoles, cancel out or do not cancel out, to determine if the whole thing is polar or not.
gotcha.
Okay, anything else? All right, so what we're going to go through now for the rest of this chapter 4 are 2 progressively complicated but progressively informative theories about bonding in covalent molecules. So we know at this point that when you make a covalent bond, any bond that involves nonmetals, you're going to be sharing electrons. Now the question is, how exactly does that sharing work? What happens to the electrons? Are they what kind of orbitals are they in, how do they distribute themselves around the molecules, and so on. And that's what this section is going to cover, are some theories about bonding. So the first one we're going to cover is called valence bond theory. And that's what we're going to try to get through today, is called valence bond theory. And the key concept of valence bond theory is that it more or less assumes that what we have is overlap of atomic orbitals. Now, as we'll see, sometimes we have to modify those atomic orbitals as part of valence bond theory, but basically what valence bond theory says is you have atom A that has some atomic orbitals, atom B has some atomic orbitals, and if they're going to form a covalent bond where they're sharing electrons, the atomic orbitals from atom A and atomic orbitals from atom B are going to overlap with each other to make that bond. So basically this is still very much what's called a localized approach. It assumes that the atomic orbitals still belong to one atom or another, and it's just that two of those orbitals are going to actually overlap in space to be able to form a covalent bond. And so if we have simple diatomic molecules like H2Cl2 or HCl, what we can think about for valence bond theory is just where are the valence electrons in these molecules, and then those are going to be the orbitals that we typically assume are going to overlap to form the bond. So if we have H2, we know that each hydrogen atom is just a 1s electron, valence electron. There's only one electron in hydrogen, it's in a 1s orbital. So if we take two hydrogen atoms and overlap those to make H2, what we're going to do is we're going to take two 1s orbitals, one from each hydrogen atom, and we're going to form an overlap region. We're basically going to smush these together where the two 1s orbitals overlap. They should be ideally the same size and still spherical shape, but as you guys know, I'm a terrible artist, so bear with me. So you're going to have two overlapping 1s orbitals, and the two shared electrons are going to be sort of in that overlap region, in the part of space where the two orbitals overlap with each other. But this valence bond approach still assumes that we have a 1s orbital on this hydrogen atom and a 1s orbital on that hydrogen atom, and they're just coming close together so that those two orbitals overlap with each other, but it's still two separate orbitals. And now the electrons are in a region that is shared by the two separate orbitals to make that covalent bond. All right, so again, you have two overlapping 1s orbitals to make your H2 molecule, okay? If we do Cl2, it's still a diatomic molecule, but now the valence electrons are a little bit different. So each chlorine atom would have, from the periodic table, a 3s2, 3p5 configuration. So in this case, the 3s orbitals are filled, so we can't overlap 3s orbitals to make a bond because there's no unpaired electrons in those to share. So because we have a filled 3s orbital in both of these, we're going to use an unpaired 3p electron to overlap and make the bond. Okay? So the way that would work is for each chlorine atom, we have a 3p orbital that has an electron in it. And we're going to combine that with the second one that's also a 3p orbital with an electron in it. So each chlorine has one unpaired electron in its 3p orbitals. We're going to bring two of those together. We're going to overlap the two 3p orbitals. And so you're going to get two overlapped 3p orbitals. And in the region where the two 3p orbitals overlap, you're going to have two shared electrons. And so that's, again, valence bond theory, taking two separate atomic orbitals from two different atoms and overlapping them to make the covalent bond. In this case, it's going to be 3p orbitals because that's where the unpaired valence electrons are in the chlorine atoms that you can then pair up and share when you overlap the two orbitals. If we go to HCl, it's also possible, as we'll see, to use two different types of orbitals. They don't have to be two 1s or two 3p orbitals and so on. So in HCl, the hydrogen has its unpaired electron in a 1s orbital, as we saw. The chlorine has an unpaired electron in a 3p orbital. And so if we're making a molecule like HCl, we would take the hydrogen 1s and then the 3p from chlorine, which each have the unpaired electron in them. And we're going to overlap these two orbitals to make the bond. So you're going to have the 1s orbital from hydrogen overlapping with a 3p orbital from chlorine. I didn't do a very good job of drawing that. And again, in the region where the two orbitals overlap, 3p from chlorine, 1s from hydrogen, you're going to have two shared electrons to make a covalent bond. So this would be your hydrogen, and that would be your chlorine, oriented in that way. So valence bond theory assumes that atomic orbitals, one from each atom, are going to overlap with each other to make a covalent bond where the shared electrons reside in the space where those two orbitals overlap with each other. Now this works fine for simple diatomic molecules like these, H2Cl2, HCl, but if we start getting to more complicated shapes, we can't just simply use atomic orbitals anymore. And hopefully this picture and some of the other ones I'll draw will explain why. So let's say we have the molecule BeCl2. We would predict from VSEPR that this makes a linear geometry. Now the problem with this, though, is if we look at the valence electrons in beryllium, the central atom, we know that each chlorine is going to have an unpaired electron in a p orbital that can overlap to form a bond. But if we look at the central atom, which must also then overlap with those outer atoms, so each beryllium needs to overlap, have some sort of overlap with each of the chlorines to make a bond with it. Beryllium has a 2s2 and then 2p0 valence configuration. So the question is, if beryllium just has two paired electrons in s orbitals, an s orbital being a spherical orbital, how is it possible for that to overlap with two chlorine atoms to make a linear molecule? And so the problem is, in many of these molecular geometries that are more complex than just two atoms, you can't really just invoke the atomic orbitals on the central atom. You have to invoke what are called hybrid orbitals on the central atom. So what we do in the process of that's called hybridization is we're going to take the 2s orbital and we're going to mix it with the 2p on the central atom. So basically we're going to take one of the s orbitals from the central atom, one of the p orbitals, and hybridize them to make two identical orbitals. Okay, so we're going to hybridize s and p. We're going to make what are called sp hybrids. So we're going to basically blend these two orbitals together. We're going to leave two of the 2p orbitals untouched. So we started with 4 valence orbitals on beryllium, and we're going to end up with 4, but now 2 of them are going to be a blend of s and p. And what this allows us to do is now the 2 valence electrons in beryllium are in 2 separate orbitals, and these two are going to form so basically we formed 2 new hybrid orbitals on beryllium that are oriented 180 degrees apart as they are for sp hybrids, and that allows them to then overlap with the 2 chlorine atoms and make a linear molecule. If you were just using the 2s orbital on beryllium, there's no way that you would predict that that could happen. Now to give a little bit more of a picture of how hybridization works, let's go through a couple more examples. So again, some of these details are to help introduce the topic, understand what it means to hybridize, which is basically mixing orbitals on the central atom to make new orbitals that have different shapes and different orientations. The key thing we're going to have to be able to do is predict what the hybridization is of the central atom, which we'll get to in a little bit. Now let's go to a different geometry. So if we had BF3, so the type of orbitals we're going to form here via hybridization are called sp2, and this is going to be anytime we have 3 electron groups on the central atom. So in the example of BF3, the geometry is trigonal planar. And the boron atom here, which is at the center, has a 2s2, 2p1 valence configuration. So that's the valence electron configuration for boron. And again, looking at that valence electron configuration, there's no way to easily say, well, how would it ever form a triangular shaped molecule from that? It only has one unpaired electron. Even if we put all the unpaired electrons into the 2p orbitals, we know that the 2p orbitals are oriented 90 degrees from each other. So how could you form 120 degree bond angles, a planar trigonal structure, if you're just using 2s and 2p orbitals? So what you have to do to be able to do that is you have to mix the s and p orbitals together. And this time we want to form 3 identical bonds, so we're going to mix 3 of the orbitals together. We're going to take the 2s orbital and we're going to mix it with 2 of the 2p orbitals. And so because we're going to hybridize again, which is mixing orbitals on the central atom, the 2s and 2 of the 2p orbitals, in this case, to be able to form 3 identical bonds in BF3, what you're going to get is a set of 3 identical orbitals that are called sp2, because they came from 1s and 2p orbitals, that's why I call them sp2. and then one of the two p orbitals is still going to be empty. So then what happens here is that the three valence electrons that are in boron are going to rearrange themselves into these sp2 orbitals, and then these three unpaired electrons that are now in three identical orbitals, all 120 degrees apart, these are going to overlap with the outer fluorine orbitals to form the three identical bonds. And then what you'll have in the molecule also is an empty 2p orbital on boron. So this 2p orbital is going to remain empty, but these three sp2 orbitals are going to have electrons in them, and they're going to overlap with electrons from the fluorine to make the three identical BF bonds that are arranged 120 degrees apart. Yes?
So essentially what we're doing is we're taking, I guess, two of the slots in the 2p orbital and just donating it to the s orbital?
You can think of it more like a mathematical combination. So the 2s and 2p orbitals are wave functions, or mathematical functions, and we're basically taking linear combinations of those wave functions to make new wave functions that are defined for the central atom, which are all at the same energy in this case and all have the right orientation to make the correct structure. So it's kind of more like not so much a donation, but more of like a blending of the orbitals, kind of like going back to the rhinoceros and horse analogy. If you mix a rhinoceros with a horse, you make a unicorn. And so the hybrid orbital is kind of like the unicorn. It's a combination of two parts that are blended together to make something that's new and different. It's kind of like a combination of the two.
Why is there still an empty 2p?
Well, we have to keep the same number of orbitals. So we always have in boron a 2s and three 2p orbitals. And so if we're going to only mix together three of those to make sp2, we have to still have the 2p that's still there. If we mix together all four of the orbitals, we would have made, as we'll see in the next slide, sp3 hybrids, which are the wrong geometry for bf3. So basically, depending on what the geometry of the molecule is going to determine what the hybridization is of the central atom. And so in this case, if you want to have a trigonal planar geometry, you need to have sp2 hybridization. With sp2 hybridization, a 2p orbital is going to be left untouched, and it's going to be, in this case, empty. The 2p orbital can also sometimes be unhybridized. As we'll see, it's going to also be involved in forming a different type of bond that we'll get to a little bit later today. Okay? Yep.
Could you go more in depth to how you have 1, 2p, and 3 sp orbitals instead of the previous example where it's 2 and 2?
More in depth why we have 1 and 2?
Or really how we have 1 and 3 on this one and then on the previous example.
Yeah, so what we're doing here is it depends on how many of the p orbitals we're mixing with the s orbital. So in all of these hybrid orbitals, we're going to take the s orbital that's on the central atom, and we're going to mix it with 1, 2, or 3 of the 2p orbitals to make new orbitals that are oriented in the correct way. So obviously there's a lot of math behind this that I'm skipping and is beyond the scope of this course, but basically if we want to make a linear molecule like BeCl2, we need to take 1 2s orbital and 1 2p orbital. So if we're mixing an s and a p, that's going to give us 2 new sp orbitals, and that's going to leave 2 of the p orbitals untouched. So we started with 4 orbitals over here, a 2s and 3 2p's. We mix 2 of them together to make sp hybrids, and then we leave 2 that are unmixed as just 2p orbitals. But then down here what we had was, in this case, to make a trigonal planar molecule, we needed to have 3 hybridized orbitals. So we're going to take our 2s orbital and mix it with 2 of the 2p orbitals, and then you're going to get a set of 3 sp2 hybrids, and then you're going to have 1 2p orbital that's still unhybridized that we didn't mix together with the s orbitals.
So basically,
Oh, go ahead.
it basically just comes down to the geometry of whatever molecule.
Yeah, the main thing you guys are going to have to be able to do, which we'll get to a little bit later, is if you know the electron group arrangement in the molecule, which is related to its geometry, be able to say what the hybridization of the central atom is. I'm trying to go through a little bit of the details about how hybridization works here. I don't have as much time to do that as I would like, so I'm skipping a lot of details that might make things more confusing than they need to be. But basically what we want to get together is that we're basically mixing together atomic orbitals to make new hybrid orbitals that are then going to be responsible for forming the bonds with the outer atoms. Yep.
Can you explain why you multiply?
Because in this particular example, we're mixing a 2s orbital with 2 2p orbitals. So the hybrid orbitals we're making are going to be a blend of an s with 2 p's. And so that's why we're using 2 of the 2p orbitals to do that, to make these 3 orbitals. If we want to make 3 hybrid orbitals, which is what we need for a trigonal planar arrangement, we need to mix together 3 atomic orbitals. So we're going to use the s and 2 of the p orbitals now to make that. And so basically what these look like is you're starting with a spherical s orbital and then 2p orbitals that are oriented 90 degrees apart from each other. Remember, the 2p orbitals, the atomic orbitals, are x, y, and z directions, 2px, 2py, 2pz. When we make the hybrid orbitals, we're going to have our central atom, and it's going to have basically one hybrid orbital that goes in this direction, has a little bit of a lobe down here, another hybrid orbital that goes in that direction, has a little bit of a lobe up here, and then a third hybrid orbital. But the point being is that when we hybridize the orbitals, we get 3 orbitals that are 120 degrees apart that are a mixture of s and p. And so what they kind of look like pictorially are 3 identical orbitals that are kind of in between s and p. They have one large lobe and then a small lobe of the opposite phase, but they're oriented. The key point is that they're oriented 120 degrees apart in plane to be able to make a trigonal planar molecule. Okay. All right, and then the last one that I'll cover in this level of detail before just giving you what the really important information is sp3. So in this case, if we wanted to do methane, CH4, we will predict that this is a tetrahedral molecule, AX4. And so if we had carbon, again, energy increasing bottom of the top here, if we have carbon as our central atom, it's going to have 2s and 2p valence electrons. And once again, the valence electron configuration of the central atom does not give us a good idea of how this molecule would form, because in the valence electron configuration for carbon, we just have 2 unpaired electrons. They're arranged 90 degrees apart, but we're going to form a molecule that has 4 bonds all arranged 109.5 degrees apart. And so the only way to make sense of how this would happen is we're going to hybridize, again, the orbitals on the central atom. We're going to take, in this case, we want to make 4 identical orbitals to make CH4, 4 identical CH bonds. And so we're going to hybridize all 4 of these atomic orbitals on the central atom to be able to do that. So we're going to hybridize the 2s orbital plus all 3 of the 2p's. And when we do that, we're going to get 4 identical orbitals that we call sp3 because they were formed by blending together an s orbital with 3 p orbitals. Now there are no unhybridized p orbitals because we've mixed together all 4 of our atomic orbitals to make our 4 hybrids. Remember, we're not creating or destroying orbitals when we do this. We're just sort of blending them together in different ways. So if we start with 4 atomic orbitals on the central atom, we should end with some combination of 4 hybrid and atomic orbitals. In this case, they're all hybrid orbitals, and they're each going to have 1 electron and then 1 valence electron that would then overlap with hydrogen's valence electron to make the 4 identical bonds. Question back here? Does this relate to the Aufbau principle? To some extent, yes. So basically what we're doing when we hybridize is we're changing the relative energies of some of the orbitals. Basically, the hybrid orbitals are going to be in between the energy of the atomic orbitals that are mixed together to make them. There's sort of like a conservation of energy at play here, where the sum of the atomic orbital energies will equal the sum of the hybrid orbital energies plus whatever atomic orbitals are not left. So in this case, we're going to get 4 orbitals that are all at the same energy. And so when you put the valence electrons into those orbitals, you're going to put 1 in each orbital to basically follow the Aufbau principle and Hund's rule to maximize unpaired electrons. And then that allows you to take these 4 unpaired electrons and overlap them with 4 hydrogen atoms to make 4 identical bonds. All right, was there another question in that same area? Yeah. You know I'm a terrible artist, but okay. So what this looks like basically is what we're starting with, as I said, it's not too much different than up here with BF3, with a trigonal planar. What we're going to form, though, is we're going to form on carbon a set of 4 sp3 orbitals that are arranged in a tetrahedral arrangement. So you're going to have sort of one that goes up like this, one that goes in that direction, one that goes there, and then one that goes sort of back into the page. So it's hard to draw that in 3 dimensions, but basically you're going to have one orbital pointing in each direction of the tetrahedron. All 4 orbitals are identical, and each one sort of looks like each individual hybrid orbital, whether it's sp, sp2, or sp3, looks kind of the same. It's going to be one large lobe from the overlap of the s and the p, and then one small lobe where you get partial cancellation of the other 2p lobe with the s orbital. And so every hybrid orbital looks qualitatively the same. The relative size of the lobes depends on whether it's sp, sp2, or sp3, whether it has more s character or more p character. but they all sort of have the same basic shape, but then the set of hybrid orbitals that you make is going to be, their geometry is going to be correlating with the geometry of the molecule that you're forming. So if you're forming CH4, which is tetrahedral, you're going to make 4 identical sp3 orbitals that are arranged 109.5 degrees from each other around the central atom, and then those would overlap with the hydrogens to make the 4 identical bonds. All right, so one of the electrons that's in each of these orbitals is going to overlap with the 1s electron from hydrogen to make the 4 identical CH bonds, and that's basically what valence bond approach is. So in this case, we're not necessarily using pure atomic orbitals on the central atom, but we're using hybrid orbitals on the central atom, overlapping with either hybrid or atomic orbitals from the outer atoms, and that overlap is going to give you that shared space of electron density where the covalent bond is residing. Yep.
So how many boxes does SP have?
SP.
Like, you know how you do SP2, SP3, like how many?
So SP has 2 identical SP orbitals plus 2 unhybridized 2p orbitals that we didn't use to make the SP orbitals. So it's still a total of 4 boxes, but you're going to have 2 that are hybridized, 2 that are unhybridized. Sorry, did you have another question back there? Did I cut you off? All right.
Yes.
Yeah, go ahead.
So essentially, I guess the way I'm thinking of it, just to make sure, is it's like a Lewis dot structure, but instead of thinking of the atoms being shared, we're thinking of the orbitals where the electrons are.
Yeah, so this whole picture is talking about the orbitals where the electrons are localized that are going to be involved in making the covalent bonds between the atoms.
So it's just a Lewis dot structure on close to look, essentially.
Yeah, it's looking at basically the electronic structure of a molecule. This is the first theory that's going to go into that. Basically, how are the electrons arranged in a molecule? As opposed to in a single atom, which we did in chapter 2, now we're talking about how are the electrons arranged in a molecule. All right, any other questions on this before I move on? Now, those details, as I said, are probably a little bit advanced for this course. We're not going to ask you too many questions about them. The key thing you have to be able to do is, if we give you the formula of a compound, in addition to now being able to drawing its Lewis structure and predicting its geometry and predicting its polarity and all that stuff we've covered up until now, one of the things you have to be able to do is predict the hybridization of the central atom. Okay? So, and this is all going to be determined by the steric number of your central atom, which is the total number of electron groups on the central atom. Okay? So the electron group arrangement and the hybridization have a 1-to-1 correlation with each other. Depending on how many electron groups you have is going to determine what hybridization you need to be able to accommodate those electron groups around the central atom. So if your steric number is 2, meaning you have 2 electron groups on that central atom, it's very easy to predict the hybridization. A lot of people are shocked when I show them how easy this is. So basically, steric number of 2 electron groups on the central atom. The available orbitals for hybridization are an s orbital, 3p orbitals, and then 5d orbitals. In reality, we never use more than 2 of them. So these are the available atomic orbitals in the central atom that could be hybridized. Again, in reality, we only use no more than 2 of the d orbitals. If we have a steric number of 2, meaning there's 2 electron groups, we need to hybridize the first 2 orbitals. So we have 2 orbitals get hybridized, which makes sp hybridization, and this correlates with a linear electron group arrangement. If the steric number is 3, if there's 3 electron groups in the central atom, we need to hybridize 3 orbitals. So we're going to take an s and 2p orbitals to hybridize a total of 3 orbitals. And this becomes sp2 hybridization because it was an s and 2 p's. And that's going to be trigonal planar. Steric number of 4 electron groups, anything in the tetrahedral electron group arrangement. We need to hybridize 4 orbitals, so we're going to do sp3, a total of 4 orbitals that need to be mixed together on the central atom to make sp3 hybrid orbitals that can then arrange themselves to make a tetrahedral molecule. All right, and then the next 2 that will go that are a little bit higher than that, 5 and 6. 5 electron groups, 5 orbitals need to be hybridized. So it's going to be s, 3p's, and 1d for a total of 5 hybridized orbitals. We call that sp3d, or sometimes dsp3. Those don't mean anything different from each other. Now, this is one of those points where I'm starting to... So... I think I don't know if I've given you the definition yet of what a model is. Remember, this is one model for covalent bonding. Now, the general definition of a model is a lie designed to help us understand the truth. So when I start invoking d orbitals in hybridization, I'm kind of lying to you guys. If you look at the molecules that would actually have sp3d hybridization, the d orbitals are basically not involved in the bonding. But this is a model to help us understand that. There's more details to that are beyond the scope of this course. But for the purpose of this course, if you have 5 electron groups, you would classify this as being an sp3d hybridization, and that corresponds to the trigonal bipyramidal electron group arrangement. So anytime you have 5 electron groups. And then finally, 6 electron groups, which is as high as we went. You need to hybridize 6 orbitals. So you take an s, 3p, and 2ds to give you a total of 6 hybridized orbitals, which then becomes sp3d2 or d2sp3. They can be written in different orders, but they mean the same thing. And this is the octahedral electron group arrangement. All right, so predicting the hybridization is, I think, very simple as long as you get a Lewis structure that's good enough to tell you what the total number of electron groups is on the central atom. You take that many orbitals and hybridize them, and that gives you what the hybridization should be. And it always goes S, then P, then D, if you need them with the higher, going beyond the octet rule, you'll need the D orbitals, supposedly. All right, so any questions on how to predict hybridization? That's really the key part of what you have to do on homework assignments and tests, as you'll see. So let's just end with a couple of examples of how to do that then on 2 different, actually probably a little bit of time, so we'll do these 2 examples and see if we have time for the rest. So let's predict the hybridization of the central atom in COCl2, carbon being the central atom in that case. So if we draw the Lewis structure for COCl2, what we should get is this. We're going to have to draw a double bond between carbon and oxygen at the end to make sure that we complete the octet on the central atom. Now, whether or not we had that double bond or not, we would still predict the same hybridization, because if we look at the central atom carbon, it would have an AX3 E0 arrangement, meaning that it has a total of 3 electron groups. Remember, for AXE notation, we don't care whether it's singly or doubly bonded. It still counts as just 1 electron group. So our central atom has 3 things attached to it, total number of 3 electron groups, which means that we're going to have to hybridize 3 orbitals. So for carbon, you can only go up to sp3. There are no d orbitals available for carbon. You can't go beyond 8 valence electrons. And so to make a steric number of 3 electron groups, we need to hybridize 3 orbitals, which means this becomes sp2 hybridization. All right, so anytime you have 3 electron groups on the central atom, you're going to have sp2 hybridization. Now you might be wondering, and we're going to learn this here in a second, what happens to this extra p orbital? So if it's sp2 hybridized, we have another p orbital here that we didn't do anything with. As we'll learn, that's going to be involved in forming the double bond. Okay, so the hybrid orbitals, the sp2 orbitals on carbon, are going to form a bond each with each of the outer atoms, and then the unhybridized p orbital will form another bond to make the double bond with oxygen. That's something we're getting to in a second. For now, though, just to predict the hybridization, you would get sp2. And then for this one here, complete the Lewis structure and predict the hybridization of all the carbon atoms in the following molecule. So again, the shortcut that we sort of talked about in the context of exam 1, and it's going to come up again in the second exam as well. If we're completing Lewis structures like this, that tend to have carbon, hydrogen, oxygen, nitrogen, and so on in them, the pattern we're going to want to follow is that carbon is going to tend to have 4 bonds and 0 lone pairs. Hydrogen will form 1 bond always, so don't do anything else with that, or it'll make me upset. Oxygen is going to have 2 bonds and 2 lone pairs. And then nitrogen, 3 bonds and 1 lone pair. I did that in a weird order, but these are the patterns that we're going to typically follow for these more elaborate Lewis structures to save us some time from having to count individual valence electrons. And by following these patterns, we will ensure that everything that wants to have a complete octet has a complete octet, and we minimize formal charges and basically have 0 formal charges if we follow these rules. So if we go through this structure here, this first carbon already has 4 bonds, 1, 2, 3, 4, so we don't want to add any bonds to this one. But if we go to these next 2 carbons, they each have 3 bonds. So to fix that, we're going to draw a double bond between them. Now they're both happy with 4 bonds. This carbon already has 4 bonds, so we're not going to touch it. If we go to this carbon here, right now it has 3 bonds and is bonded to an oxygen that has 1. Carbon wants to have 4 bonds, oxygen wants to have 2 bonds, so we can fix that with a double bond there. and 2 lone pairs on oxygen. And then finally down here we have 2 carbons that each have 2 bonds. This one has these 2, this one has those 2, and so we can make them both happy with 4 bonds by making that into a triple bond. Now they each have a total of 4 bonds, 1 triple bond between them and a single bond in either direction. And then to get the hybridization of each one, we just have to look at the total number of things that are attached to each carbon atom in the structure. So this first carbon atom has 4 things attached to it, 4 total groups, so it's going to be sp3 for 4 total groups. So that's going to be sp3. This one here and this one here, they both have 3 things. They're bonded to this carbon, bonded to the next carbon, bonded to hydrogen. Total of 3 electron groups makes them each sp2. We're just counting the number of things that each carbon is attached to assign its hybridization. This carbon also has 4 different things attached to it, so it's going to be sp3. This one here, 1, 2, 3 things bonded to it, so that makes it sp2. And then these last 2, they both just have 2 things attached to them. This one bonded to this carbon and this carbon for a total of 2 things. This one bonded to this carbon and this hydrogen for a total of 2, so that makes them sp hybridized. So this molecule has all 3 possible hybridizations for carbon, sp, sp2, and sp3 in those different combinations. So again, predicting hybridization is just a matter of completing the Lewis structure and then counting the number of electron groups that are present in each place. All right, so what we're going to end with today is defining the types of bonds that can form. So there's two types of bonds that can form when we form covalent bonds. So the first type is called a sigma bond, Greek letter sigma there. And these are bonds that are formed by end-to-end overlap of hybrid or atomic orbitals. The types of overlaps that I drew previously with sort of 2 orbitals coming together and overlapping in the middle, that's what you would call a sigma bond. We didn't really formalize it like that before, but that's what it is. It's just 2 orbitals coming together end to end. And it can involve atomic or hybrid orbitals. So both types of orbitals can be involved in sigma bonds. And what it means is then that the electron density in that bond is greatest in between the 2 nuclei that are bonded to each other. And it's going to be along the bond axis. So basically, in between the 2 nuclei, you're going to have the greatest electron density for a sigma bond. So the orbitals that are involved, as we said, are going to be atomic and or hybrid orbitals, some combination of those 2. But a key point, though, is that when we use hybrid orbitals to form bonds, which we very often do in these types of structures, the hybrid orbitals will only form sigma bonds. We're going to give you another bond type here in a second, but hybrid orbitals are only going to be involved in the formation of sigma bonds. All right, and so we've kind of drew some examples of these, but you'd have like 2 s orbitals coming together with their respective nuclei. And you're going to form, if you're making a sigma bond between those, you're going to have this, again, overlap region in between the 2 nuclei, and you're going to have a region of electron density that's greatest in between the 2 nuclei that are bonded to each other for a sigma bond. Or if we did it with 2 p orbitals, a sigma overlap of 2 p orbitals is again going to be a situation where we're going to put the 2 end to end with each other and have some overlap region in the middle. And then you're going to have this part in between the 2 nuclei being there and there at the center of each p orbital. You're going to have a region of electron density in between there where the 2 orbitals are overlapped. So that's what we mean by sigma bond. It's just 2 orbitals coming together head to head. The other type is called a pi bond. So these are the only two types we're going to talk about. There's a fourth type of bond called delta bonds. If you take the other course that I teach, which probably zero of you will, if you took that course, we'll talk about delta bonds, but we're going to just in this course talk about sigma and pi. And a pi bond is a side-to-side overlap of orbitals. So sigma is head-to-head, pi bond is side-to-side. When we draw those, it'll be clear to see the difference. And in this case, you're going to have it's going to result in regions of electron density above and below the nucleus, above and below the axis between the two nuclei. So it's going to result in regions of electron density above and below the bond axis. All right, so the orbitals that are involved in forming pi bonds are going to be only unhybridized p orbitals. So as we said, if you have sp or sp2 hybridization, you're going to have either 2 or 1 p orbitals that are unhybridized. And one of the things that those p orbitals can do, although they don't always do that, they can overlap to form pi bonds. And so the way they do this is that, as we said, a pi overlap is a side-to-side overlap. So you're going to take 2 p orbitals that are arranged like this, side to side, and you're going to overlap them. This is going to be your bond axis here between the two nuclei, but the overlap between the p orbitals is going to be above and below that axis. So you're going to line up the like phases, and you're going to have overlap above and sort of below the axis, where the electrons are shared sort of in that direction, above and below. So this is referred to as a pi bond, where the electron density is now above and below the axis between the two bonded nuclei. And it has to use unhybridized p orbitals. Those are the only types of orbitals that can form pi bonds. S orbitals cannot form pi bonds. Hybrid orbitals cannot form pi bonds, only p orbitals. And then the last thing we'll cover today is how many of each bond do we have? So if we have a structure given to us or that we've drawn, how do we know how many of the bonds are sigma or pi? And it's actually pretty simple to figure out from valence bond theory. So what valence bond theory includes is the idea that for single bonds, anytime you have a single bond in the structure, it's going to be a sigma bond. All right, so all single bonds are sigma bonds. In other words, any bond with a bond order of 1 is going to be a sigma bond. All right. Now, if we have multiple bonds, these are going to consist of one sigma bond and the rest are going to be pi bonds. And because we're restricting ourselves to the p block of the periodic table, we can only have single, double, and triple bonds, which means that if we have a single bond, it's sigma. If we have a double bond, bond order of 2, we're going to have 1 sigma and 1 pi. If we have a triple bond, that's going to be 1 sigma and then 2 pi to make up the total of the 3 bonds. So when you have multiple bonds, one of them will always be sigma, the rest will be pi bonds. So double bond is 1 of each, triple bond is a sigma with 2 pi bonds to make a total of 3 bonds. So then finally, if we want to look at a structure like the one we just dealt with earlier, I think this is the exact same molecule, we can also then ask how many sigma and pi bonds are there. And so if we go through this structure, every bond that is a single bond is sigma. So we're going to have sigma, 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 sigma. All right, so all of those single bonds, the ones that are bond order of 1, drawn with just one line, are a sigma bond. And then the ones that are multiple bonds are going to be 1 sigma and the rest pi. So this double bond is going to be 1 sigma and 1 pi. This double bond is going to be 1 sigma and 1 pi. And this triple bond is going to be 1 sigma and 2 pi's. So if we're counting the total number, counting is probably the hardest part of this question because there's so many of them, we should get 15 sigma and 4 pi. So out of the 19 bonds in this larger molecule, 15 are sigma, 4 are pi. The only time you have pi bonds is when the bond order is greater than 1. All right, so that takes us to the end of valence bond theory. What we're going to cover on Wednesday of this week is the more advanced bond theory, molecular orbital theory, which We will only apply it to very simple molecules, but it does give us some additional information that we can't get from valence bond theory that we covered today.